Professor Peter Herman is from the Electrical and Computer Engineering, University of Toronto. He has been, he holds his PhD in laser and laser physics from University of Toronto, 1986. And then he joined the famous Institute of Laser Engineering in Osaka University. They're also good for high power laser. He, in his lab in Toronto, he leads a large group of PhD and postdoc research associates, and his research focus on using femtosecond laser or laser in general to make lightweight devices, while photonic sensors, and all different type of laser material interactions he is going to show us today. Professor Herman has published over 300 journal and conference paper, and he is an OSA fellow, holds several patents. He had a spin-off company called Fine Lasers, and that has been successfully sold to one of the laser giants called Raffin. So I heard today's students have asked how to get rich. Okay, let's welcome Professor Herman.
Well, thanks very much. I think I'm better to advise you on how to do good research. All right, so it's a great pleasure. Thanks for the introduction and nice words. It's a great pleasure to be back in Rochester. I haven't visited this area for decades, I think 20 plus years. So I have a couple of slides actually relate to work that was done by a Canadian student researcher earlier on, so I'll connect it to my theme. So this is a recognized optics center. When I was a young student, we heard Arizona and Rochester were the top optics places in the world at the time. So I certainly have been influenced by research in this area, and would like to know, I guess, return the favor and tell you about the research activities we've been doing recently, as well as in a bigger picture, a kind of vision of these opportunities that lasers can give us. So the talk is meant to be a little provocative in that we're not relying on the usual absorption of light by materials. We're using special physics to drive interactions, and out of this enabling new types of manufacturing to be possible, new types of devices to be built into materials that is not just on the surface, but internally in materials. And just the importance of optical materials and glass as things we touch and play with every day, used for entertainment, iPhones, displays, as well as medical diagnostics. It's in our lives everywhere. Having new manufacturing tools there is turning out to be really important today. So let me give you that story. Firstly, just a bit of an overview slide. So usually when I give talks, it's not so close. So we're just across the lake, and it's an easy drive. Toronto is the largest city in Canada. It's a business center, very active and fun place. About half the people born in Toronto proper are non-original Canadians. They came from other countries. So it's a highly diverse and interesting place. We're famous for the CN Tower. Actually, today there's many more buildings here. We're in a building boom. We've been interested in terms of some of the leaders we've selected in the past. This was our bad boy, Mayor Ford, who got on the late night circuit. So you may remember seeing him. And then we have other leadership, which is more inspiring and I think in tune with Canadian values. So we're just next door. Come and visit us. And just to give you an idea of the ethnic origin of Toronto, you can see Chinese is number 2 against English. Probably going to surpass that. Canadians means, I guess, people don't want to really say or don't know their origin. And you can see it's really a welcoming cultural mix. All right, so, oops, I'm hitting the wrong button. So, back to the research. So in Toronto, I've been there for a long time now as a professor in electrical and computer engineering. We have a diverse group, as you can see here, and the mantra that I created about more than 10 years ago is really the center of my interest, that I'm interested in light, and I'm also interested in optical devices. And it's really interesting that you can start with a light and modify an optical material to make useful devices. That's the theme. And so I'm going to walk through giving you an overview of how that research works. And let me start with a picture like this. This is a slide as part of developing the spin-out company where we exploited this self-focusing nonlinear effect to modify and cut glass in ways that are incredibly fast and now commercially used. So we have damage here, and I want to take you back historically as you're looking at this picture and think back to the development of lasers. So let me move to this slide. So this is a slide created by Gerard Moreau when he was here in Rochester, and a Canadian student, Donna Strickland, who's now a Canadian and a professor at the University of Waterloo, made a really important discovery. Prior to that, as lasers were being invented, created, and then improved and powered, there was this period of time where the focusing intensity, the brightness that you could focus the lasers to, plateaued. And it's because you really got to this limit where you could no longer scale up lasers to bigger and bigger areas because there's diffraction limits, etc. Amplifiers would have problems of self-focusing damage, creating defects that would burn and damage the optics. How can you create higher intensity without damaging material? So material processing was happening regardless of trying to engineer and avoid it. And so it was the invention of chirp pulse amplification by Donna Strickland, guided by Gerard Moreau, which led to this revolution where you could now take higher and higher amounts of energy and compress them to very short pulse durations so that you can make these high intensity sources. So you wanted to avoid material processing to allow these lasers to come about and to explore very interesting physical directions. So this is very old work, and it's taken about 20 years or more for this technology to become a kind of everyday, keyless, reliable, reproducible technology. To run with these kinds of lasers early on, you needed to be a PhD laser physicist because you were tuning these things. Things were burning and breaking down. And people told me you will never see femtosecond lasers in commercial applications because they were so hard to use. Of course, they didn't know that humans are very inventive creatures and we can improve technologies. And so today, in fact, these kind of power levels are routinely available and tunable, and you don't really need to worry about the laser, you can worry about the interactions. So we turn this all upside down now. We're back to having lasers which can damage materials, but the idea is not that we want to damage it, we want to control the kind of interaction and make useful devices out of this. So the physics here is strange and unusual and a huge opportunity. Let me then spend a bit of time talking about how we could use these short pulses and why they're very special. So let's go back to the very big challenge, the mantra. If we want to use laser light and modify glass internally or on the surface, we have to remember we're starting with an absorbing material. So let me throw up an equation which talks about the polarizability of a material. How far does the electron shift relative to the nucleus of an atom or in a molecule, driven by the electric field. And so chi tells us the response of different materials. And generally in here, chi has a real part and imaginary parts which are associated with the refractive index, which we would use every day in Snell's law, and an absorption, which is zero by definition of a transparent material. So when you're presenting light to this material, all you can do is refract it, but you cannot absorb it by this linear process. So how do we get around turning on absorption? We have to go to higher order terms. All right, so if we look at chi 2, it's not that hard to prove that if we reverse the direction of of energy, of electric field, you get a conflict mathematically, which means that there's symmetry inversion in the material, and you cannot make second order interactions with the material. We have things called doubling crystals. They don't have inversion symmetry, but glass does have inversion symmetry. It just turns out it's hopeless that you can drive second harmonic effects inside the bulk of glass. So that's a well-known effect from nonlinear optics. So what you need to do is you need to turn on the so-called Chi3 process, third order. These processes are enhanced by the third power of electric field. So if you double intensity, this could be 8 times more strongly interacting. So how do you get strong electric fields? Well, focusing obviously is one approach, but the other approach is that there's a certain amount of energy you need just from thermodynamics to reach a threshold of modification. The idea is to take that energy and apply it in shorter and shorter pulse durations. And so when you get down to, say, picosecond or in the femtosecond domain, that amount of energy is more than enough to turn on and drive both real and imaginary parts in Chi3. So out of this then come refractive index effects with these short pulse lasers. Refractive index might be a Kerr lens nonlinearity, which leads to self-focusing, forming filaments and other effects. Or it may turn on absorption directly, so that in the focus volume, confining a Gaussian beam into a depth of focus and beam waste, you can get a controlled absorption. And so now that's where the opportunity comes in. But it's not so simple. So what other effects should we be thinking about as if you want to come into this field and really take advantage of these lasers? Well, okay, we've got spot size omega naught and a depth of focus. It's not symmetric. That might be a problem that you need to counter by doing some beam shaping. When you enter a flat surface, you have something called, strangely, spherical aberration. So Snell's law breaks down and the focus gets distorted. So as you focus deeper, you have distortion effects. Before you get to the focus, you can get self-focusing. The focus position can move up, it can filament, and so even before you get to the focus, there's several distorting elements taking place. Next, as this intensity is rising in the focus, Chi3 has multiple modes of interaction. There's dozens of pathways that this can turn on that seems complex and maybe discouraging. So you can drive, for example, a multiphoton absorption, but then an electron is generated, a free carrier is generated. Those in turn can allow avalanche ionization. And then further, you're modifying the material so as the latter part of the pulse sees this modification, it takes a different path than the first part of the laser will follow. And so, in fact, this modification plus these effects cycle around several times that it just seems like a dog's dinner that you really cannot get a reproducible or good outcome, you might think. It seems impossible to control this wild, ultra-fast interaction. So a lot of damage was seen this way decades ago. People are aware of this physics. And what we want to do is, say, a material scientist making useful devices, is that we need to modify the material after the absorption. Is it possible to create, for example, helpful defects, to anneal, to arrange bonds, to make refractive index structures, nanobubbles, memory devices, etc. There's a range of opportunities depending on how you set up the energy to turn on these effects. And so it does turn out that these processes, even though they're complex and multipath, the way you present the laser, its shape, its pulse duration, its wavelength, the numerical aperture of your lens, all those things can be made to control the outcomes and turn on or off different elements out here. So I like to, in fact, think of this as a magic hat that out of Chi3 you can pull out and turn on these processes in appropriate ways. And I've got several examples of my own research experience in this field, and others, many others are seeking out these opportunities. So no longer is it damage, it's actually controllable modification that is a big opportunity. So let me give you a very broad overview, and then I'll come back and talk about some of the opportunities in this process. And so if I go back to really near the start of my research work, I started working with Marchbanks in physics, Robin Marchbanks. He's a graduate from the University of Rochester, and he was building a picosecond laser. And so I said, well, let's machine holes with that and study this effect. And I'm going to talk about our serendipitous discovery and my first patent with him on heat accumulation effects. That was just not expected. second thing, this hole that's formed in the side view of the glass, while that's very important, you see a filament has formed. The laser is self-focused and modified this, and that was actually the secret behind Abbas Hosseini spinning out phi laser, allowing very fast cuts and separation of glass. Eric Mazur at the University of Harvard, or Harvard University, talked about very tight focusing and doing three-dimensional modifications in glass, high-temperature glass. So these are very permanent. You could do these memory devices, and that was really interesting. But if you look closely at modification, for example, in fused silica, you end up forming nanobubbles, as well as with polarization control, you can align these self-assembled gratings over many pulses. So this internal morphology consists of, say, positive index changes that look white in this sort of micron scale view, and on the nanoscale underlying that are birefringence effects, because these are directional modifications, and porosity, which leads to stresses and index changes. It looks kind of ugly, but the outcome is you are making 3D devices with some benefits. So with all of that, for example, if you want to avoid this morphology, one way to smooth things out is to go back to these high repetition rate effects, this heat accumulation effect, and you can get these very smooth waveguides. This is an end view of a laser scan where you have a nice, fairly smooth positive index change here, and the symmetry of this is sufficient to make pretty low loss waveguides, for example. Ivan Zhang in my group discovered serendipitously again that if you modulated this while scanning, you could make gratings in here at the half wavelength periods. And so Bragg grating waveguides were formed simultaneously with the waveguides in that approach. Rod Taylor in NRC Canada just added acid to these glass structures and found the acid would etch quickly along these grating planes controlled by polarization. So we took that effect and showed that you can make this microstructure, I'll come back and say more about it, with really high resolution. It's an inverted woodpile structure. So what you see here is refractive index changes that are patterned into waveguides or gratings, or 3D structures, which is a neat processing technology of very high resolution. And I'm going to tell you about how we combine these together to build a combination of functional components inside optical fibers, which are used in telecommunications and optical imaging for biology, etc. And we added waveguides and open cavities, etc., and calling this lamina fiber. So this is just sort of one narrow view. There's many other directions people are taking with this technology, and it's basically additive manufacturing and subtractive manufacturing with resolution at the wavelength of light. So I think this is going to really transform how we make things and how we could invent new ideas for glass. At the end of the talk, depending on how much time I have, I'd like to also introduce another modality where, for example, in this case, we have filaments following the laser. Here we're making these little thin plasma discs, and we're opening up nano structures in thin films of glass. For example, in CMOS technology, we have oxides present, and we're trying to invent a way to make nanofluidics and do lab in a film, which is another mode of interaction that I'll tell you about. That's a lot of fun. So the point is, in this, you're driving nonlinear absorption through Chi3 polarization. It looks like a wild west of energy wandering wanton around multiple directions, but in fact, you can get reproducible events. You can see the structures here, and now it can be tuned and made into manufacturing methods. And this is actually happening now. In the last 5 years, there's been a boom in femtosecond lasers being used in manufacturing all sorts of bio to commercial and microelectronic devices. So it's turning out to be a good field. So let's go now and talk about the invention of this heat accumulation effect. So this is a very fun topic. I was collaborating and learning more basic physics with Marchbank's group. We're drilling holes, and we found that in glass, once we got to a micron deep, the glass would crack. And we thought, wow, that doesn't look very good. We can get high precision machining in this zone, and then side shatters. This was done at a very low rep rate. Laser And we had trouble finding these spots under the microscope. So out of that challenge, we thought we could apply a different mode of the laser. This custom-built laser offered bursts of hundreds of pulses in very short duration, separation times of 26 nanoseconds. And so we thought, if we hit it with this pulse to get this, that's just 4 pulses. If 400 pulses hit that, it should be a really easy to find structure with lots of cracks. What we saw was a big structure, but there was no cracks. The funny thing is, how does 4 pulses make cracks, and this avoids cracks altogether? And so when you think about it a bit and realize that the community missed the idea that there's a thermal process associated with femtosecond processing. All the literature before this said it's a non-thermal process, too fast for thermal physics. Well, what happens is, after a first pulse, you've got a heated form of glass that's cooling. It doesn't cool infinitely fast. And the second pulse, if it arrives fast enough, is hitting heated glass. And we know that glass, like all sort of brittle materials, becomes ductile as the temperature rises. And so that ductility assists and prevents cracks from propagating, from forming and propagating. And so this heat accumulation effect under so-called burst modes became a patent application. It actually led to a license. We didn't do it very well, didn't get rich or anything, but it now, in fact, 20 plus years later, is now an important industrial process today because the lasers are reliable and it has this enhanced machining effect that's really a lot of fun. So there is this parameter of repetition rate that's very important. I'll come back to talk about repetition rate being a control parameter that people didn't really think at the time would be useful. All right, so with that process then, we are able to cut holes very quickly in silica glass. This is now sort of emerging as a really important need in biology, as well as in electronics for doing multi-layer stacks of connected electrons, vias. And so this is having a big influence. I mentioned that the filament that's forming simultaneously with this process is a whole different opportunity. So this is Herman's self-focusing, and basically with a Gaussian-shaped beam, the center of the pulse slows down, and so the wavefront distorts, and then it self-focuses, and when you get to the focus, it stays focused over long distances. And if you get it right, you can see that this white zone shows a positive index change. It's a compressive zone, and it creates stress. And so we discovered a way using bursts to enhance this effect, that we can make really long filaments, one burst at a time, and then eventually we could make these curtains of filaments at meters per second. And in, for example, Gorilla Glass, which is already stressed, those filament tracks just pop the material apart. Or in other cases, you apply a little pressure and the plates separate. And so this technology took quite a few years to develop, but eventually it's now today replaced in diamond saws, which seems like a cheap technology. But diamond saws has a lot of damage. It has a kerf width that's wider than this process. And so now there's these $1 million laser machines making filaments and all sorts of transparent materials, separating them. And it's really fun to see something discovered in a lab and then translated over some hard work into real processes. So there's our patent and just some pictures of that early work. And I'm not going to say much more, just that was a fun digression and led to something very important. So it turns out after cleaving, the surfaces under high magnification show the filament tracks, but this is much higher quality than generally diamond saws can do, and faster and lower cost. So we're trying to improve the filament with, I don't really have time to talk, I think, about spatial light modulators, but so one of my PhD students today is playing with spatial light modulators. We're trying to reshape these wavefronts to non-spherical wavefronts, shape the Gaussian to non-Gaussian, and it's actually improving the plasma. It's also improving the waveguides that I'll tell you about briefly today. And you can do parallel processing in here. So there's new modes of beam delivery that is another control element that's becoming a popular research topic. And I think also industry is picking up on this today, that beam shape is critical to further enhancing and improving and steering the laser interactions inside the 3D volumes that that we want to manufacture in. So, for example, we're making filaments that separate and can be combined into offsets, etc. So you could steer the cleaving process or even make new kind of microfluidic elements, for example. So this is sort of future work. You have to invite me again to talk more about this, but just want to say that's a really powerful tool today in this field. All right, so I'm going to just move back to waveguides and mention this work that was done by Shane Eaton, who's now in Milan, a professor there. And we are showing the effect of heat accumulation in waveguide writing. But here, this is a static exposure where 4,000 laser pulses were applied here at 1 megahertz. And then we increased it by 10 times, so this is 40 million pulses. And you can see that there's maybe a doubling of the size with an increase of number of pulses by multiple orders of magnitude. So it's not a big change with huge changes in exposure, right? So 4,000 to 40 million pulses. What do you think happens if I repeat this exposure but at slower rates, at lower repetition rates? If I go to 1/10 the repetition rate, 100 kilohertz, notice that all the features get smaller. And in fact, the number of pulses is a weak control parameter on the morphology size. So in here, the laser focus size is about this size here, the size of the green laser pointer. And those are heat-affected zones that accumulate with more pulses to grow bigger and bigger. With repetition rate increasing just 10 times compared with many orders of magnitude on the number of pulses, we have a much bigger effect on the morphology taking place here. So when you're selecting a laser to control processes, you can't just think about the wavelength or the pulse energy or a scan speed. Repetition rate is hugely important. And this is not only important for machining holes, as I showed earlier, but also in the morphology internally inside the material. So I'll skip this talk, but it basically is a heat accumulation effect, and then we'll go on. So let's then move to another serendipitous discovery. While Ivan Zhang was trying to sort of finalize some of his work and get his thesis written, he made a serendipitous discovery while he was scanning and forming waveguides, taking advantage of these ideas. But what he had done is he was reducing the repetition rate and increasing the writing speed, and he eventually saw a spectrum that didn't make sense. And so this is an important point in any research project, is something strange comes up and you ask questions about why it's there. And this, of course, then leads to patent opportunities and new types of manufacturing tools. So it turned out that when these structures were made, for example, like this turns out to be a waveguide where these separation distances, when they're half a wavelength, you now have a waveguide which is also a Bragg grading filter. And so optical filtering, like electronic filtering or any kind of filtering, is very important. We want to tune devices. And so we're able to build these waveguides simultaneously with this, have made several publications over 10 years ago now and a couple patents. And here's how they look. So along here you see parallel laser form waveguides, the white zones, and you can see the scattering of light at optical wavelengths. You can see the blue to green, so showing that there's a structure there on the scale of wavelengths. And so when you pass light through this, you'll get a notch filter here in transmission or in reflection. And what we did is we just with computers shifted the writing speed and shifted the Bragg resonances. So we have narrow band filters formed this way arbitrarily. So this is a really important tool. It's a 3D process, and we did things like chirp the spectrum, which is important, say, in telecommunication applications. We narrowed them with pi shifts. We added features to make birefringent effects, and so we showed quarter wave and half wave polarizers. If you bring the waveguides close together, they act as directional couplers, so you can switch light from one path to another path, which would be wavelength sensitive. And so these are sort of well-known optical effects that have been applied in fiber, have been applied in planar circuits, and showed here's a way to make them inside bulk glass without any multiple step processing, and some examples of the spectrum, say of a cascaded Mach-Zehnder interleaver, for example. So this technology is now a really popular area of research around the world today. There's hundreds of researchers looking at it. So we're lucky to be very early in the field. And the kind of devices that you make here could be are used today in telecom and making unique sensors, making biomedical devices, and we've certainly played in quite a few directions this way to enable optical circuits and spectral control and switching control to be possible here. This is really an exciting area. These are some examples of other groups that are in here, just to show you that it is a big field. People are working on quantum optical kind of applications here in Germany. Making photonic lanterns is a spin-out company that telecom companies are interested in. So there's a whole range of 3D opportunities that is not possible to do these things so reliably in planar or fiber circuits. Okay, so that's refractive index changes. So I mentioned that you can get nanogratings forming under certain conditions with certain materials, and here's how they look. This is the Rod Taylor group in NRC Canada. With laser polarization pointed this way, the mode we use for waveguide writing, it turns out the nanogratings assemble on about 200 nanometer, 300 nanometer periods. If you apply Lowell acid, you can open them up. So it turns out that there's a rarefaction of the material, and there's molecular oxygen-rich zones. And if you apply acid to that, the acid flows through this and etches that zone very quickly. So you can open up these tracks, particularly if you align the gratings this way, you can open these up and do buried channels. So that was this sort of work done from Ottawa, and many groups, including our group, has picked up on it. For example, this is a buried channel in fused silica glass where we form these nanogratings, open them completely, but then we also, by running devices this way, we could form waveguides that would not etch. And so we now have a microfluidic device with optical sensors integrated together, and you can integrate these in 3D. The neat thing with these planes aligned this way, when you fully etch this open, these planes are very flat. They're 10 nanometers. So they're not optical quality, but they're certainly a very small fraction of a wavelength. And so we have pretty low losses on coupling between these waveguides across that zone. So with that, you can make a lot of different structures. If you make parallel laser tracks and then chemically etch them, you can control the shapes of devices that etch. So for example, here are the laser modification zones where laser tracks were in and out of the screen. After etching, you could open up rectangular structures as shown here. You have to align them to join. You have to align them appropriately, or maybe you want separate zones. But the neat thing is you can adjust the exposure parameters, and this is this inverted woodpile structure. And I just want to say these are laser scans that are layers of, let's say, log patterns this way, then this way, and this way. The chemical has opened those up, so it's inverted this, and you're left with this almost impossible to make form of glass. These members, these little membranes here are just 2 microns big, and it's very intricate. This is formed over 100 by about 80 microns, and it's a channel along the surface. So this might be useful as a chromatography type structure. All silica, very biocompatible, that really would be hard to make any other way. So this slide is meant to demonstrate the possibility of structuring glass 3D for multiple uses as MEMS devices, as filters, etc. So here's a picture of where we applied this to make microfluidic channels, cross channels. We want to make little plugs and demonstrate electrophoresis, separation of materials. And there's one level and a second level. So this is a multi-layered level. And it'd be really hard to manufacture that with wet lab techniques because it's always at a surface. The channels will cross each other and mix fluids. So here's a little picture showing plug formation. So you'll see that with voltages of these liquids, you're sending rhodomine dyes forward or backward with really good resolution control. The roughness of the walls here turned out not to be affecting the resolution of the system, and you can do multi-levels on a chip. So I think the potential is really strong for new manufacturing methods. So we've worked with industry partners. We're making holes to assist with assembling fibers, for example, making glass plates like this. So we laser structure and then assemble fibers in this into control precisions. And the company we did this for said our resolution's at least 5 times better than anything they've seen before, and it's an all-glass package. So that's sort of a micro-scale kind of immediate benefit of this kind of laser processing that's improving new manufacturing methods. And what I want to do next is move this technology into the fiber. So not just make those templates or not make 3D circuits in fiber, in bulk glass. Why do we want to go to fiber? So let's first think about where do we use optical fiber and why. So in any kind of communications, when you have a cell phone, you're wireless, but it goes to a tower and then goes to fiber. We're all interconnected. Fibers go pouring into, say, Google, and all the data is there stored on chips. And so we're bringing fibers up to silicon chips. It's the most efficient, low-cost way to transmit information. It's also used to inspect inside our bodies for medical procedures or to look into dangerous places like nuclear reactors. There's no electricity, but a lot of valuable information is going back and forth through fibers. It's flexible. But fibers are kind of used in a very simple form. It's just like an A to B transmission. So you have this core waveguide, and for telecommunications, it's just a single core currently today. And what we thought is we should enhance the properties of the fiber. Only about 1% of this fiber area, what happened to my laser? 1% of the fiber is actually waveguiding. The rest is just glass to give it some more structural integrity. And so the idea here was to use lasers and add these 3D optical circuits to improve functionality. So while in telecommunications you want to go from A to B, along the path you could think of adding sensors. So the Internet of Things is about measuring and connecting things together, and one idea is distributed sensing, to measure whatever you want to know along the path of the pre-existing fiber waveguides, or to build more functional surgical tools. So when one of my colleagues that we're researching, when he's treating aneurysms, he spends hours under x-rays trying to find the path, and we're making steerable sensing fibers based on some of these technologies here. So there's a whole host and range of important applications to pursue. So we published, a lot of this early work was published in this book chapter, if you're interested to read about that. So let's talk about the challenge though. If we're going to add this value to the fiber, then we need to have really high precision to focus the laser into the fiber. And what we need to keep in mind are some of the problems. Firstly, in a fiber, it's a cylindrical shape. So that's astigmatism. So when you focus a laser through this, you're going to end up with 2 foci. You're going to get a line focus in X and a line focus in Y. That's a lot different than in the bulk glass. Secondly, when you move the laser left or right, this surface is bending, and so the position you're mapping to is highly distorted. And so the overall interaction is really terrible, especially when you're not focused at the center. There's an asymmetry there, but when you want to write in different places, these distortions prevent this from working. So what we worked really hard developing was the use of an immersion lens. So an immersion lens, we use oils which have refractive index matched to this surface. It means that that surface disappears optically. So the laser can then be pointed anywhere in here without distortion, and guarantees that the focus has the same shape. Remember all those nonlinear effects I talked about? Well, we really dismantled those, and we're able to get reproducible modification anywhere in the area of the fiber from core to outside. So that was really important development. We slide this bead of oil along a fiber. This is 4 inches of strip fiber. They're clamped in place, and then we learned to get about 1 micron positioning resolution. So we can make structures relative to the pre-existing core waveguide to 1 micron. So with all of that, then we could go back and ask, can we make waveguides that connect with the core? Can we open up structures, build microfluidics to do some kind of sensing applications? And in fact, it all does work. So there's a cartoon depiction, just 3D, showing a lens, and I don't know why my laser stops working. Okay, maybe the battery's getting good. So then there's a picture of the green frequency double femtosecond laser focusing through the fiber. You can see the shapes there. We use that to help align. What we can try to do is make laser form structures in the core, for example, to make fiber brag gratings. If we write them near the core, we can make it multi-mode and build well-known devices like multi-mode interferometers. Or if we go a little further away, it becomes a directional coupler. And so we almost gave up on this research. It was really hard to get this alignment to work. And I remember Jason Grenier, who was driving this, just really struggling. And I was thinking, oh, I've got to put my energy somewhere else. But eventually got it to work. And then we did a lot of this. I'll show you a couple examples here. I've never had so many invited talks in my career out of this work. So I was really happy. It's one of those places where working hard and persisting pays off. So I'm really happy about the results here. And this is just a small sampling of some of the things we can do. So in the core, well, we and other groups can easily align the laser and make gratings. So what we did is we formed grating waveguides outside the core. Right? So that's nice. We can now drive an idea of something called fiber cladding photonics, making things in the cladding around the pre-existing core. But the problem is that when you bring these waveguides close, well, I'm struggling with my pointer. Is there another one? Okay, thanks. I'll try to use this for dancing. Okay, there we go. So, thank you. So, this coupling isn't automatic, and the reason is that you need to have the same effective index. The refractive index of the core waveguide is this effective value here, 1.446, just a bit more than that. The glass around it has this refractive index, and the germanium core has a refractive index higher. So there's the starting point for the core waveguide. There's the starting point for the silica. When we laser write waveguides, we need higher energy, and so we can increase the refractive index of the waveguiding effective index like this, but it never reaches the effective index of the germanium doping. And if we modify the germanium, it just increases as well. So we have this difference, and if we were to look at the theory, this is called beta mismatch, and so the coupling coefficient is dramatically reduced based on these differences. The only way to counter that is to increase the coupling coefficient. So if you make the waveguides closer that you form, then this K value gets really big, and then you can get strong coupling approaching maybe 90% or so. So there is some optical engineering that is really important. There's Jason, quite a few years ago now, and he worked with other people in my group to make cross couplers, S couplers, directional couplers. They all worked, and it's a really good story. I'll skip this one. So for example, with S couplers, there's the core waveguide, there's the S waveguide, and as a function of radius, so changing the radius of the laser waveguide, you can see that the light in the femtosecond waveguide is growing as we make the radius smaller. So you can get light in and out, and that's a good story. It's important to be able to tap it in and out. And if you make a cross coupler, you vary the angle of this waveguide, and at 2 degrees, you see a huge drop in the power in the core waveguide. And if you measure the light that goes into the cross-coupled waveguide, we've gotten up to 78% or so light crossing over. So you can get appreciable amounts of light, and now think of making cool devices. Here is a kind of hybrid multimode interferometer directional coupler. If we stand parallel and close, in this case 6 microns from the center, here's the power that you see as a function of length or time, and you get this oscillation, which is exactly what a directional coupler does. And it also has this additional interesting effect. It looks like we're going to this 3 dB point. At this point, we have some birefringence. And at this point, we've actually done polarization splitting. So one polarization is in the core waveguide at this point. The other polarization is in the laser form waveguide. And so in this, we can consider building all sorts of useful devices. You can pick points like A to make a 3 dB 50% splitter. You can go to point C to make a polarization splitter. Or you could try to couple all the light out at point B. So you have a lot of choices now on design to get light in and out of the core. So it really is flexible. And you can go to this reference here to learn more about that body of work. All right, so getting light in and out is key. And now what are some of the devices? Let's show an example of a Mach-Center interferometer done by Luis Fernandez. He's now at Oz Optics using femtosecond lasers to make fiber devices. And so he made a coupler, and he spiraled it in a helical path around the core and then rejoined in here. And so if you get about 50% coupling between these 2 points, then you end up with something called a Mach-Center interferometer. So Mach-Center interferometer means if you put light in here across the spectrum, you'll see, this isn't exactly right, I dropped that graph, but you get a sinusoidal pattern of light with wavelength. That's not what this is. So what we do is we go to the quadrature point and sense here, and then here's a little picture of this fiber suspended by magnets. So what we do is we twist the magnets, and then we record the light at the quadrature point. And as the helical path tightens up or relaxes, it shifts the wavelengths, meaning the intensity is shifting. We record that, and so we now have a directional torsion sensor for the first time done in a single fiber. So that's really convenient to build in a single device this new kind of sensing arm that was only done with multiple fibers before. So I think it's just a demonstration of one of many, many opportunities for fiber sensing. These could be shape sensors, which could be important in surgery, as I mentioned, or going into dangerous places. We demonstrated a 3D shape sensor using similar ideas. It's really a remarkable new manufacturing tool.
Are you saying the optical path is different for the one arm than the other because of the twist?
So it is longer, but it turns out because the refractive index is much lower in the silica, this is actually a shorter path. Physically it's longer, but optically it's shorter.
Does it change because of the twist?
Yeah. Yeah.
That's the
Well, even if you go parallel and have equal lengths, the refractive index is higher in the germanium core, so it's actually faster in the laser formed waveguide. So if the refractive index is higher in the core, okay, then it takes longer.
Twisting, one arm has to become longer than the other.
Yeah, so it's refractive index times the physical length. So normally this would be a longer path, right, because it's spiraling around. But the refractive index in the glass is lower than in the core waveguide. So it actually does the opposite of what you think. But in the end, there's a net optical path difference, and that gives the cosine wavelength pattern. And then when we twist this fiber, that helical path is getting longer or shorter due to the twist. That's torsion. And so this is a torsion sensor. All right? Is that?
You mentioned the magnet. You mentioned magnet. It has nothing. There's nothing about magnets.
It's keeping it straight and suspended,
it's just a weight.
and it has inertia, so it's just twisting like a pendulum. That's all. Yeah. Yeah. People do magnetic sensing in ways,
Right,
but that's not here. Okay. Yeah, you're trying to make it more complicated. All right. How much more time do I have for the talk?
If you want to leave some time for questions, you
Yeah.
already have a couple of minutes.
Oh, there's a clock there. So I should finish in about 5 minutes or so. Is that about right? Okay. So I'm going to skip a bunch of slides and I'm going to just talk about the lab and fiber, and then introduce the thin film processing. So just a minute here. So Mohawk's just joined Intel. He tried to combine the microfluidic etching. So he etched out a Fabry Pro resonator. So that's chemically etched. It allows fluids to come in and out, so we could do refractive index sensing by Fabry-Pro effect. He made a cross coupler and then curved the waveguide, and so reflections from this were brought back to our sensor. He built in a Bragg grating into the core to be a temperature calibration sensor, and then what we did is we heated this to calibrate with, and measure temperature with the Bragg grating, and we also bent this, put it in a beaker. We can measure curvature, and with refractive index, we're able to successfully measure this. So here's some pictures of devices we're etching out of fibers. So we have really good control in aligning them with the core. Here's the same picture, and so what you see is you see a Fabry-Pro, you see a fiber Bragg grating resonance for measuring temperature, and this is the Fabry-Pro. And if you bend or change the refractive index of the cavity or heat it, these shift. And then we could decouple all of these things, and we measured the refractive index of water as a function of temperature, corrected for the bend of the beaker it was in, and we got the classical results. So it's kind of neat that you can make all those measurements from a fiber that's just 125 microns in diameter. And the neat thing is you could repeat these elements along a fiber to distribute it, to be able to do this over long distances. So we can now start to dream about some really cool things. So that's the groundwork, we would say, for lab and fiber being established here. I'll just show this result. This is actually writing through the buffer, and we've taken the spiral path and chemically etched it, and then part of the channel goes through the core waveguide. We put in fluorescent beads. It turns out you can sense the beads, and this is just a quick video for the possibility of cytometry in a fiber. And so you're going to see a bead moving in here. And there it is in the center. And this doesn't show the fluorescence, I don't have the video here, but it really lights up, and you can detect the fluorescence along the fiber core. So you can excite and detect along that, and we're just trying to put a paper together on that kind of result. So a lot of really cool stuff. Okay, so I'm going to just flash through maybe 2-3 picture shows here. So I promised to introduce this idea of what is now an interferometric processing. So this different approach. So in thin films, this is another serendipitous discovery. For example, CMOS technology, you have silicon oxide on silicon. And we know that when the laser comes, it has a strong reflection, so it can interfere with itself as it's coming in and on reflection. And there's also another small reflection at the air boundary. So you end up creating interference fringes. And it turns out that if you apply the laser pulse short enough, the materials are right, that you can get absorption in disks. And we found a way that we could have plasma disks exploding and digitally open up the film on half wavelength spacing, as you might expect. So no one actually, people knew this interference effect would happen, but no one ever saw this kind of morphology. So let me show you the kind of neat structures we can make. I'll skip. So I'll point out one thing. These plasma disks are following the interference pattern of light, but they're narrower because of nonlinear absorption. So these plasma disks are about maybe 40 nanometers thick, and this depth of focus is several microns. So we're really downscaled the interaction zone along the laser propagation. So these are flat pancakes, and when they explode at the right amount of absorbed energy, then they peel open the material in these unique ways. So let me skip this. So here's a sequence of images where you see at a threshold fluence, one layer ejected. Then you see, with a Gaussian beam, an inner second layer ejected. And this diameter opens up, and you can see layers peeling off. This is good quality film. I thought the student was making crappy film when we first saw this stuff, but it turns out it was this interferometric effect. And so it's a really neat effect. And you can see that the material survives. There is part of those half wavelength thick zones still stuck on. So this is a really new kind of cleaving, horizontal cleaving method in thin films. When you remove fractional layers, you can do coloring. Each of these spots were made with a single laser pulse. So you could do 1 million per second with today's technology. So you could think of new ways of patterning and marking, which is really important for identifying different manufacturing processes. I'm going to show you some of the most recent results by David there. So he did some angle studies to try to enhance or diminish the effect. So that works, but I don't have time to do this properly. But let me just show you the coolest morphology. So we've really got control. Here's ion milling of this structure here. So you can see that multiple layers, multiple disks have exploded. They're competing with each other in explosion. Some disks are flying completely off. Others form these incredibly thin bubbles. This is pure silica. It's probably like 150 nanometers thick. It's enclosing a zone that might be vacuum. You can see the peeled layers like a burst bubblegum spread here. And inside are voids. And so the morphology is really cool. And what I think is really important, going back to the shaped beams, so Isan and Jiansao working together have made a uniform line focus with this. And here's the structure. So we're about 20 microns, pretty uniform now. And what we are showing is that we can make nanofluidic structures. So it's much smaller than the size of a cell. That's 130 nanometers high. And we're trying to run this tens of microns on the surface of silicon. And so I think if my dream comes true with this, then we can do nanofluidics. We can study perhaps DNA level, protein level material over CCD and microelectronic technology, today's everyday silicon technology, just by growing thick oxides and punching the laser in appropriate places. This might be a really important area, I hope, to make new kinds of sensor devices. So that is sort of the last thing I squeezed in. I'm skipping all this, and I'm going to conclude. So I think, let's conclude here. I want to say that there's a lot of science in all of this and a huge opportunity where I introduce things that I've discovered and other people are playing with. There's much more to it in here. The heat accumulation effect turns out to be important. Other people are experts on self-focusing and nanograins, which we've exploited. There's interference effects that I showed you in the films. You can present laser light in really unique ways in transparent materials and make them more valuable by drilling, texturing, scribing, name it. I hope I stimulated some new ideas for you in here. So there's optical circuits, there's microfluidics and their integration, and there's fiber cladding photonics, lab and fiber, lab and a film. I think these will indeed come true with time and more research, and hope I've motivated you to take a look at this direction. And to just remind you that there has to be magic here in the end. But directed magic, or so that there's an intuition that you can have, I think, and really invent more things. This is still a new field and a lot to be done. So thanks so much for your attention. Look forward to answering your questions.
For the direct rating application, how much does using oil affect the speed limit of the processing?
Yeah, we haven't pushed that. So I don't. So you really would have to be a fluidics expert to think how fast you could go. But I think we're nowhere near a limit for that. But in the fiber, we're moving less than 1 millimeter per second. It's very slow. In air, we've done things up to 1 meter per second, where you need really high speed and long travel ranges because of acceleration zones. So I imagine if you go too fast, you might have like bubbles and cavitation forming. I don't know, I haven't thought about where the limits are, but I think we're really far away from it. I was really surprised that droplet of oil would slide across the fiber surface. We also do it over bulk glass, so it'll slide over the surface of glass, and it lasts quite a long time.
I recall my history. I think the first person to report laser damage was named Herman.
You better tell me the reference.
I think I was like in 60 or 61 at an OSA conference. There's no relationship there.
Probably not. That's really funny. Yeah, it was, I think for probably 30 years, it was all considered negative effects, these short pulse lasers, and it only turned around in the 90s, I would say.
Have you looked at vortex beams?
Yeah, we're thinking of whether we can use them, but I know a lot of people playing with them, and you can impart morphology effects into the film. So there's a lot of fun there. I'm sure it's important.
So what about the sidewalls for the Athlon device? You have made inside the fiber.
How flat is it?
Yes.
Yeah. So when you, so the writing laser focuses down. When the polarization is like this, these planes assemble this way. These surfaces are flat, quite flat, to say 10 nanometers, maybe 20 or so. But locally, over small areas, they're 10 nanometers, so really, really amazing. But on the bottom, they're maybe 200 nanometers roughness, 200 to 300 nanometers, so submicron roughness. And that's because the end of the planes are, the morphology is more abrupt there.
What about your student teams? Like they're from electrical, computer engineering, or you have students from chemistry and material science?
Yeah, so students, I kind of like an engineering physics student, kind of like my undergraduate degree, because someone who's got an applied sense has stronger sort of math and physics background than say electrical engineering. So those are probably the ideal students. But we've had like a nano program at Toronto. I've taken students from there. I take our ECE students, so they take photonics, and they may be weaker on the fundamental science. But I also get international students who come from a variety of different departments. So I mean, I would look at people from material science, maybe more mechanical than electrical engineering traditionally, but I need someone who really understands Maxwell's wave equations, so electrical engineers fit in. I'd like them to be able to handle optics, and then physics students, of course. Occasionally a chemistry student are the best choices.
The same here, I have students from all these majors.
Yeah.
Not chemistry yet.
Okay. It can work. Yes.
For the topic you talked about the life in the fiber, how do you detect well, introduce the fluids across that fiber? How do you detect the refractive index change in that system?
Yeah, so we would add, you can just buy different, you can mix different solvents together, and there's well-known techniques for that, or we often buy just index oils of different varieties, and just we apply them with micropipettes to different parts of the fiber, so they go in. You have to be careful when you design these channels, because if you just drill a hole into this top plate and then you make a tunnel and come out, what will happen is you just get a meniscus, and the liquid won't flow out. So you have to actually build tapers, try to keep angles less than 45 degrees, let's say. Then the fluid and the right chemistry, the glass can also, if you put a weak acid, like even vinegar, it wets water better. So there's these sort of well-known microfluidic ideas that you need to pay attention to. So if things go wrong, you might get bubbles trapped in bad design. So we went through pains of all those things as well. But that's an important practical question to pay attention to this. So if you follow that, then capillary force just draws liquids through these channels, and that's the basis of cytometry, for example, that I've used and other people I collaborate with use.
No other questions? Okay, so if there's no other questions, there's a reception for this. Coffee and cookies.
You can ask me more questions there.
You can ask more questions there, that's right. And let's thank our speaker, Professor Herman, one more time.
Next.